Hello and welcome back for another presentation in your California geography course. This time we're going to introduce the geology of California. Now this is a beginning point for much content that can be provided about the diversity of our landscapes here in California. But this one in particular is really going to just inform us a little bit about the provinces, a little bit about the underlying geology, how it's studied, and some of the main time points in California's past that are quite notable and observable. That being said, let's start with the image that I have right on the front screen. I know this is my title card, but I just think this is really interesting, especially for those who either live in Santa Clarita or have been to Six Flags Magic Mountain. This is a geologic map of Santa Clarita, and what I love is just looking at all the different fractures and faults that are within this area that create really the beautiful landscape, the mountainous landscape and canyons that we have in the region. The one that I like the most is obviously the Magic Mountain Fault, which is right here. We can also observe part of the Pelona Schist and the San Francisco Fault, B Canyon Fault. I mean, sure, this may not mean a whole lot to you because you don't know much about the geology, but these are the place names and sakes of the locations that I live in. What's interesting, what I think is interesting, is the colors that have been chosen. These colors all represent different types of rock. Perhaps they're metamorphic or sedimentary, and they'll be labeled as such. So I really do suggest that as you work through this content, really take advantage of all of the different geologic realms and videos that are out there to learn more about the rock formations that we observe. That being said, let's jump into the first slide. So let's just begin with the geologic complexity of California and really learning the understanding pieces as to what geology is. Now, geology is the science devoted to understanding the Earth's physical structure, its substance, its history, and the processes that act upon it. California's geologic history is very complex, as most of the state did not even exist as a coherent piece of the Earth's crust until just recently, geologically speaking, that is. Geology is still very active in the development of features and can be observed in mountain building, earthquakes, and other deformation across the landscape. What we need to understand first is that when we speak of geology, what is geology? It's really the science of understanding the fine-tuned elements, the minerals, the rock formations. As a geographer, we look at the world spatially. So we look at big picture stuff. We look at the large faults, and we look at the mountain ranges and the volcanoes and the landscapes. And as a geologist, that's when I get to bring out my little loop lens, and I sit down and I start looking at the chemical compositions within the rocks, the processes, the heat, the pressure, what was needed in order for this to develop. And I look more at that fine-tuned, finite information that is really almost unobservable in the field. It's so small in some cases, and otherwise it can be quite large. Now, we know that California has a dynamic past and future, and we'll talk more about that later in this presentation, specifically about the geologic past and some of those really iconic time periods. But then this is a great point to start bringing in just the idea of geologic time. As humans, we don't understand geologic time. It's very hard for us to put into a relationship what 1,000,000 or 300 million years looks like. Because we look at someone who's in their 70s and go, wow, they're so old. But really, geologically, 70 years is nothing. That's just a fractal of time in the grander scheme of not just millions, but now billions of years of morphology, of change and studies and rock. And we'll talk about some of the oldest rocks found in California as well, and trying to put dates with those. So it is complex. There are some additional resources on my YouTube channel if you're interested in more specific or detailed components of igneous and sedimentary metamorphic type rocks and minerals and other types of geology. But again, it's dynamic, and we live in California. We are so lucky to live in California because we really have all of that type of geology in your face. It's everywhere that we observe, which makes it really exciting to teach. So before we can really talk more about what's under the ground, it's best to talk about the provinces that exist above the ground. So let's begin with this next slide. So this is the physiographic provinces of California. We have been able to divide California into 11 prominent provinces. That's what's observed on the left-hand side. On the right-hand side, we're going to observe also the physiographic provinces, but we're also going to look at a very simplistic geologic map within. So as we can see on the left-hand side, California is broken into 11 areas: Klamath Mountains, Cascades, Modoc, Great Valley, Sierra Nevada, the Colorado Desert. These provinces have been decided and outlined based on its geology, based on its natural landscape and the topography, and the region, the climate. There's so many different elements that have been designed. So again, these are not your counties, these are not your cities, these are really provinces of different types of geography and geology observed in California. Now, what we can observe in the map itself is we can see that there's different colors, and that's what I love about geologic maps, is just the brilliant colors and patterns. Before I can move forward, we need to know that there is a rock cycle. You've probably heard about it before. 3 types of rocks. You have igneous, sedimentary, and metamorphic. Igneous is volcanic. It's either going to be formed on the outside or inside the earth. Sedimentary is formed by essentially sediments, so usually large bodies of water. Larger rock material and minerals, no matter what it is, breaks down, gets transported, deposited, and then lithifies, which means it turns into a rock, such as like sandstone and breccias and conglomerates. And then the last one is metamorphic. Metamorphic means it's any mineral or rock that has undergone extensive change through heat and pressure. And we can actually observe all 3 types of these rocks in California, and we can observe them throughout different geologic pasts. So the first thing I want to point out with this key is that we go from more recent to old. And we can see that the most recent material is Quaternary, which is a geologic time period, are sediments, meaning that this gray material, this tannish, whatever that is, tannish gray, represents quaternary sediments that were brought in alluvium-based by flash floods and erosion, which also imply that most of those areas must have been underwater at some point to let that material settle. What's interesting about that is if you've ever taken California Indians or other courses like that, we learned that the Great Valley, due to its geology and its very rich agriculture, proves that there was once water there and that it would have been more of like a wetland. And most of your indigenous folks in California, early California, obviously, we're talking not just hundreds but even thousands of years ago, would have been able to transport their goods via craft, which is pretty cool. So we're able to see that we have sedimentary. We also see some areas that have igneous rocks, such as the Sierra Nevada, granitic rocks, which is rocks that form deep beneath the Earth's surface. And we're also able to observe some metamorphic rocks throughout, and most of the metamorphic rocks are the oldest rocks found in California. So this kind of paints a picture of our provinces and paints a picture of our geology, lightheartedly, of course. But let's take this a little bit more detailed. So the next slide is just going to break up the first 6 provinces, and then I decided to write in a few words to describe what that region's known for. And before we kind of do that, just think about California. You have probably had the opportunity to be able to travel a little bit, to go see some of the places, the cities, the towns, and stuff like that. Think about those differences. Think about those boundaries that have been drawn because of these provinces. Do you notice a difference when it comes to the landforms, the geology, the vegetation, stuff like that? These are some things to think about. So we'll start up at the top. Klamath Mountains up in here. The Klamath Mountains are gold-bearing gravels. So that's very prominent in gold country up in here. We also have the Cascade Range. The Cascade Range is a volcanic cone system that runs from California all the way through Washington State, of which some of those volcanoes do show activity. We also have the Modoc Plateau, which is a volcanic tableland built on lava flows and tuff beds. So it is raised. We also have our coastal ranges right along here. The coastal ranges are subparallel to the San Andreas Fault and are the result of uplifted marine sediments due to tectonics. In fact, you can kind of see the line here a little bit, and that's part of the San Andreas Fault within this fault map. We have the Great Central Valley, the valley itself, which is an alluvial plain or material that was brought in by running waters itself, rainwaters and flushes. It's about 50 miles wide and over 400 miles in length. So it's a massive, massive area of which we do find a majority of our agriculture grows, as well as our milk sheds. And then we also can observe the Sierra Nevada, which is at our highest point, Mount Whitney, which is at 14,508 feet in elevation and lifting up, is a tilted fault block system. And the Sierra Nevada itself, the mountain range, is a 400-mile long mountain range that has uplifted. So imagine, the Sierra Nevada is a granite, a very unique granite. It's called the Sierra granite. It's one of the hardest rocks in the world. And so not only do you have this massive piece of rock that had developed over time, it cooled, reheated, and cooled and reheated, then it was uplifted essentially because of a tilted fault block. So you have this tremendous amount of change of uplift and erosion, which now shows us one of the most grandest mountain ranges in North America. So we can move on to the next slide, which wraps up provinces 7 through 11. We have the basin and range location, which is quite interesting. Faulting, stretching, deformation creates lakes, playas, and even Death Valley. We find that between the basin and range and Mojave Desert, we have a tremendous amount of dry areas, including Colorado Desert as well. But what's interesting about the basin and range is that we do see a lot of tension being created through stretching, that the rock is literally pulling the whole area is tearing apart, and in doing so is creating some of the thinnest crust in North America. Not as thin as the crust found at Yellowstone National Park at the site of the old supervolcano, but it's one of the thinnest crusts in North America down in the Death Valley area. We also have then the Great Mojave Desert, which is an isolated region, a desert bounded by not just the San Andreas Fault, but also the Garlock Faults. Perhaps you remember, I think it was 2019. I don't remember. There was that really big earthquake out of Ridgecrest, California, which is, the byproduct of, it's its own new fault, but it was the byproduct of stress and tension that was built up between the San Andreas and the Garlock Fault. The Garlock Fault is this guy right here, and it offshoots the San Andreas, so it shoots outward. It's right around, well, yeah, it's right about there. So it shoots out. It's perpendicular, which is kind of neat. We also have the transverse ranges. The transverse ranges are very unique. Transverse means to cut across. It is also part of the Santa Monica Mountains, but it's pretty much most of what we see in Los Angeles, part of the San Gabriels and stuff like that. And you really drive all the way, when heading down into Palm Springs area, you're paralleling that location, those mountains. And what's interesting is that I did state that they're part of the Santa Monica Mountains, which means they're also part of the Channel Islands. So the islands that are out within the Pacific Ocean at one point were connected to the mainland, but due to sea level rise has created isolated islands. And we'll talk more about the Channel Islands when we learn more about the historic biogeography and the pygmy mammoths that lived on the islands there, but I digress. And the last area that then the peninsular ranges, which is down here. Although it is a coastal area, it's actually more closely related to the Sierra Nevada as just geologically, because it's predominantly granite areas. And then lastly is the Colorado Desert, which is a low-lying desert dominated by the Salton Sea, which we can observe right here. It's a depression block between the San Andreas and the Mojave. But what's really, I think, interesting about that location is that that's within this area, especially the Salton Sea area, that is one of the locations of the oldest rocks in California. And we'll talk more about that. So I hope this kind of helps at least create a map of the provinces. What I suggest to just, when you're thinking about this and you're studying and trying to memorize these different provinces for map quizzes, is just really thinking about when you've been to places there, what have you observed to be different? And based on your interpretations of this map and your previous observations, are you able to make any correlations? Does it make sense? Have you been to Mammoth? What is Mammoth Mountain made out of? Have you been to the Mojave? Have you been to Death Valley? Have you been to the Salton Sea or the Bay Area or whatever it might be? And try to create some of those pinpoints. If you have not been to those places, maybe you haven't had that opportunity, check out some videos. I've got a handful of videos that we'll talk about later. When it comes to different provinces and different features, I have videos from all over California, but really try to create that experience within trying to relate the provinces, relate that geology and those landscapes with what the names we can observe in these outlines. So now I'd like to take the opportunity to talk about faulting and deformation. Mind you, there are classes you can take on the geology of California, and we only have a short time that we can really speak to some of this, but I wanted to make sure we started talking about the faulting and the changes or the deformation of our landscapes. So we can see that because of subduction, the Juan de Fuca and the Farallon Plates, that they would create volcanoes and massive batholiths. Accretion, or the pushing of these plates to create mountains, such as the coastline of California. Now, we've been able to observe different types of faulting. We see the uplift of plates that create mountains. We've seen transform boundaries, such as the San Andreas Fault. And we've also been able to observe in California's landscape faulting caused by other types of regions, such as dropping or basins. So the first image on the top, we can see that there's a horst, a graben, and normal faults. Horst means it's been hoisted up. Graben means it has been grabbed and pulled down. So we have areas in which the valleys are being pulled down, but the mountains on either side are being lifted up. The Sierra Nevada is an excellent example of that. It's a fault block system where the valley floor, the Owens Valley, is dropping down, and the Sierra and the Inyo mountain ranges are being thrusted up. They're being hoisted or horsted up. The difference is in this diagram is that the Sierra Nevada is granite and the Inyo are sedimentary, but nonetheless, it's the same idea. So this can also occur not just from lifting and pushing, but also from just stretching. So we also find that, even though we have a San Andreas Fault that is a transform boundary that runs, pretty much the whole length of the state, not only is it pushing together, but there are certain areas that are being pulled apart. We have to remember that, fundamentally, the North American plate is moving westward and up a little bit, and then you also have the Pacific plate that's also pushing, but also moving. And so we have all kinds of motions that are being pushed and pulled, and because of that, the rock is getting stretched and squished, pushed, and all kinds of deformation, and all of that adds additional stress and tension and energy to the rock, which we ultimately observe as being earthquakes along these weaknesses. So this is a diagram down the bottom showing Death Valley, Badwater Basin, which is our lowest point at negative 282 feet below sea level, which is interesting. That's a whole other story because Badwater Basin's in Death Valley. Death Valley at one point was called Lake Manly, and Lake Manly was one of the largest freshwater lakes in the state, but it has all evaporated, and it's a whole big story, but it's exciting, and we'll get to that later. But nonetheless, we can see that due to the valley pulling itself apart, the valley continues to sink, sink, sink. Now, luckily, due to flash floods and rains, it brings new material in and fills it up. As we can see, we have these Playa Lake sediments and alluvial fan sediments, but it's still dropping. It's dropping at almost the same rate that it's filling. But at some point, it's going to drop faster than it's filling, and then we will have incredibly thin crust in that location. So I did mention at the top specifically the Farallon Plate. I think that's really, really interesting. Let's spend a moment to talk about that. Now, most of your life, you have been familiar with the fact that we have the Pacific Plate and the North American Plate. If you live in Los Angeles or you live on the western side of the San Andreas Fault, we're still part of the Pacific Plate. If you live on the other side, you're going to be on the North American Plate. But at one point, there was one more plate betwixt them, between them, and that was called the Farallon Plate, and this was specifically down in Southern California. And what we can see in this animation, if I hit play, we can see that as the Pacific Plate is moving, it's pushing the Farallon Plate into North America. And in doing so, it was melting and pushing down and providing, due to subduction, additional material to create mountain ranges. And then the Pacific Plate would continue to grab California and start pulling everything. And then if you notice in that animation, all of a sudden we have some new features. I mean, we look at Baja California. Where did that even come from? Where was that pulled from altogether? So what we have learned is that, yes, we have the San Andreas Fault, but we have additional boundaries that used to exist, and we still have a few areas that we can observe part of that Farallon Plate, which is really, really, really exciting. Let me hit play again. So here we can see the Farallon Plate is being pushed into the North American Plate. California doesn't even look like California yet until the Pacific Plate completely pushes the Farallon Plate underneath, and then it grabs a hold of California and starts pulling it up and outward. And when doing so, look what it's doing to Nevada, Arizona, Utah. It's starting to stretch that rock out. And mind you, at the same point in time, you also have the continuous motion of the North American Plate moving. Other things to take in consideration. This is just observing one piece of this whole process. We also have to take into consideration the fact that North America has not been in the same place as it was. Everything's moving. Everything's moving. So, at a certain point in geologic history, California would have been closer to Panama than it is now. So we're constantly in motion. We know also that there have been several supercontinents, meaning all the continents collided and became one, and then they ripped apart and created individualized continents. And so we have all kinds of interesting aspects that can be observed here. Something else that's important to mention at this point, just in case you have not learned it yet, but we know that our plates, which are essentially these land masses that we live on, there's two types. There's oceanic and there's continental. Oceanic is traditionally basalt. It's denser, darker, more basaltic, essentially. And that's what our oceans are on. The Pacific Plate is part of that. The North American Plate is what we call a continental plate, which means it's predominantly made out of granite. It's a granite landmass. Are there igneous and, are there other like basalts and things? Yes, we have hot spots and all kinds of other things can accrue on the land masses, but traditionally continental plates are made out of granite. Oceanic plates are made out of basalt. Again, I mentioned the word subduction just in case you missed it. As the Pacific Plate was pushing the Farallon Plate, it subducted. It went underneath. When it goes underneath, it remelts within that molten magma, and then at that point, you get so much material built up that you create volcanoes. And we have a really fantastic volcanic history in California that we'll talk about throughout this term in these videos. A great example of still just activity today. You can see some of the hot creek. There's one in Bishop, where we can see geothermal hot springs gurgling, really boiling water, hot springs and stuff like that. We do have the residual or the remain of a supervolcano called the Mono Lake, which is a massive lake that has mostly desiccated or dried up, but it's the remnants of that and the Mono craters. So we do have a lot of volcanic history in California. Everyone's like, California's got this, earthquakes. No, we've got earthquakes, volcanoes, we got everything. And that's what really makes our landscape really so unique and beautiful. So that's the Farallon Plate. Moving forward, let's talk about just surface processes, which we'll spend some more time talking about later. But, because of these three words, erosion, transportation, and deposition, those are huge contributions and game changers for California's landscape. Erosion, the process of breaking material apart, such as weathering. Then you transport that material and then you deposit it elsewhere. Two photos. Top one, Yosemite. It's all granite, formed miles deep beneath the Earth's surface, cooled very, very slowly, massive crystals that had developed, and then rivers eroded the area, and then we had maximum glaciation. In fact, there would have been ice filled to the top. So much ice that it cut Half Dome in half as it slowly plucked and abraded and carved throughout this valley. So we can see not just uplift, but we can see tectonics, we can see glaciation, we can see so many different river action. Look at this waterfall here carving away at that granite. Beautiful landscapes. That's what we call geomorphology. Geo meaning earth, morph is change, and ology is to study. Studying how the earth changes paints a different past and future for what we observe, especially when it comes to the inland seas and ocean, volcanics, earthquakes, and more. Here's a photo I recently took of Death Valley. This is of the Badlands. It's called that because the land is bad. It's very, very, very fine-grained ash and silts. Nothing will grow. It's been capped off with volcanics. Beautiful, but we can see the erosion that happens when they do get rain, creating those nice gullies and arroyos and these beautiful landscapes that really no one else has but us. Now, I have mentioned time, that there's a lot of geology in time, and let's talk about that next. we have a very unique geologic past. This is a very simplified geologic timescale. It goes back in by millions of years until we get into 5.42 billion, and then a little bit farther, and I cropped it out. I'm more interested in the time of which we have data for California. Now, there are rocks over 600 million years old. They're very, very rare, but there are some in California, and there are some over 1 billion years old. They're found within Death Valley and over by the Salton Sea. So we actually have metamorphic rock that is over 1 billion years old. I mean, that to me, that's almost unbelievable. In fact, I went down to go see it. I wanted to touch some billion year old rock, because you just don't get to see stuff like that. You know, in most landscapes, you're not going to find that in Montana. You know, you find that in California, and that's the result of the Farallon Plate. So be sure to check out that video. But between 1 billion years to 400 million years ago, most of California would have been under the ocean until the Sierra Nevada began uplifting, and that's been observed in both the limestones and the dolomite deposits that have been observed. We found, there's many limestone deposits, especially in the Inyo mountain ranges that are, they're over 12,000 feet. That's along the western margin of California and Nevada. And we've been able to see some of those dolomite deposits that, are, again, over 12,000 feet in the elevation, but we can date that they were made out of marine sediments at one point, so it had to have been under the ocean, which is incredible. Now, the distribution of geology in California suggests that there was a tectonic plate between the North American and Pacific plate, the Farallon Plate, things that we have discussed already. We also have learned that there's been a volcanic past, and there's, who knows, perhaps a volcanic future. We do certainly see more activity, more earthquakes, and a tremendous amount of studies that are coming out of the eastern Sierra in specific, closer by Mammoth Mountain. Now, there is a very unique story in how California has its shape as it is. As we said earlier on in this presentation, that for most of California's past, it wasn't even a landmass, it was under the ocean. So, what happened and what was that timeline? And that is what we will cover next. Now, before we go, what we have, I was going to bypass it and I forgot. So I do have this geologic time scale here for you. So what we can see is that, when we talk about some of these things coming, in the future portion of this presentation, I'll make reference to some of this. And what's interesting is that we can see all of these different, timelines. The Mesozoic is really an interesting point in geologic history, specifically when it comes to not just dinosaurs, which we're not really in the Jurassic, that's a different story, but just looking at our flora and fauna, looking at our ammonites and all of our underwater creatures that have been deposited in California's history. I mean, I had the opportunity to go on an excavation where we were pulling out 300-year-old fossils out of California, little ammonites. But then again, I was also part of a archaeological dig in which we were pulling out, essentially 10,000 plus year old woolly mammoths out of the Mammoth area, which would have been found during the late Pleistocene, about 10,000 years ago. So what's interesting is we can see how this is broken up both into eons, eras, periods, and epochs, and then even sub-elements there, being early or late. And it's just a way for us to be able to, especially when we're finding stuff or rocks, we like to say, oh, well, this would have been Oligocene, or this is early Oligocene, or this is going to be Pliocene or Pleistocene and stuff like that. But that's what these names mean, just as reference. So let's look at this next slide. So let's look at the geologic timeline of tectonics. The left-hand side is a script, the right-hand side is a diagram. I'm going to read through the script as you look at the diagram. Things to observe and interpret in that diagram are not just the time periods, looking at early Paleozoic and so on, but looking at the notes that have been made here, sedimentary deposits that have been accumulated onto the shelf, looking at the ancestral Pacific Ocean, looking at the North American plate, stuff like that. Looking at those images to try to paint the picture of this past. We're looking at what has happened and where did California even occur from during the last 570 million years. So let's begin with the first one. Letter A, early Paleozoic. Sediments eroded from the older rocks exposed in the middle of the ancient North American continent progressively accumulated on an expanding continental shelf and stable ocean margin basin. Between 350 and 400 million years ago, during the mid-Paleozoic, the antler orogeny, a mountain-building event, affected much of what is now the Nevada region. Shallow seas still covered much of western North America, and what is California was mostly still deep ocean basin. So we're starting to see this antler orogeny, which is really starting to develop part of the Nevada border to California, as we'll see later, but also some stretching has been occurred during the late Paleozoic between 250 and 400 million years ago. The North American continent slowly merges with the supercontinent Pangaea. Ancestral Rocky Mountains rise and small land masses are accreted onto the western margin. During the letter D, during the early Mesozoic, about 150 to 250 million years ago, the island arc named Sonoma develops and collides with the North American continent. Then subduction changes from dipping eastward to westward. Moving into letter E, the late Mesozoic, the ongoing subduction results in the buildup of great batholiths beneath the mountain ranges all along the western margin of North America. Sediments from these mountain ranges flood the interior of the continent, flooded by the western interior seaway. Moving into letter F, the early Cenozoic. In the late Cretaceous period, the North American plate begins to rapidly override the Farallon Plate. In early Cenozoic time, subduction extends far to the east, resulting in massive volcanism throughout the Rocky Mountain range. Isn't that crazy to think that just, the result of the Farallon Plate sinking, there along the San Andreas Fault, as it were, was enough material to create volcanics as far as the Rockies and mountain ranges. I don't know, just quite fast. Just California, right? And the last one, letter G, during the late Cenozoic, 20 million years to today, North American overrides the spreading center between the Pacific Plate and the Farallon Plate. The spreading center migrates eastward, causing massive crustal extension beneath what is now known as the Great Basin region. North America overrides hot spots in the upper mantle, resulting in extensive volcanism in Yellowstone, the Columbia River, and New Mexico regions, and caused the Sierra, Rocky Mountain, and Colorado plateaus all to rise, essentially. Changes in plate boundary configurations result in the formation of the new San Andreas Fault and other regional fault systems. So we can see that there was a tremendous amount of push, pull, and turnaround to create the California that we live in today. And what's interesting about this is that the more we know about the past, it provides a better picture of what to observe and to live in the future. And and again, I think probably the most fascinating part that I observed in this model is the western, the inland seas that were created. That's cool. But the fact that the development of California affected things as far east as the Rockies, that's pretty cool. And then just think about it. Yellowstone was a supervolcano some 164,000 years ago, an eruption so big that it provided so much ash into the atmosphere that it caused a global cooling by 2 degrees. Was essentially part of the result of the formation of California. So, again, dynamic, and really exciting. So I've mentioned this before. Let's talk about some of the oldest rocks. Some of the oldest metamorphic rocks are found near the Oricopia Mountains, near the Salton Sea, and I have a video that I shared in the link. Be sure to watch it. It's just really neat. We go out there and we see 2 different types of rocks. We can see both metamorphic and sedimentary. We know we're at a boundary, and then I'm walking around and I pick it up, a piece of this gneiss, which is a banded rock because of its pressure. Compression has caused that banding, and that's one of the oldest rocks in California, over 1 billion years old, and then I can't believe I put it down and walked away. I thought I better keep this so I can share it with you, and I left no trace. I kept it there. But I thought if you've ever been down into, beyond there, on the way to the Imperial Valley, here we are, the Oricopia Mountains. It's a beautiful drive out there. So next time you're down in Palm Springs, just go through that region and head out to the other side, into San Bernardino County. But it's just a beautiful, beautiful, beautiful drive. So let's look at, again, a recap of our geologic timeline in California. We've had subduction. We had Pangaea. We had the formation of the Sierra Nevada, and essentially some even rock that was, part of the development of California is found as far north in Alaska. We had additional subduction of the Farallon Plate. We had volcanoes, which is the result of extension and then ultimately thinning the Earth's crust. And then we fast forward to the last, really, 100,000 years. So here we have this world of fire. We have this world of tension. We have this world of stress and tearing and pushing and pulling. We need to cool down. That's what needs to happen. So the last 100,000 years of California's history allotted for that to occur. So what we have here is over the last, really, it was almost 1 million years of time in which we had these mini ice ages and things like that. But over the last really 100,000 years, active glaciation of volcanoes have really changed our landscape. So here we can see some things that we recognize from earlier. I talked about the antler orogeny, the Sonoma orogeny. But looking at these different things, most of this is within the Sierra. We do see some advancements of glaciation as far south as the San Gabriel Mountains outside of Pasadena. But we can see that we had the Tioga, the Tenya, the Tahoe 1 and 2, the Mono Basin, and the Sherwin. These are all iconic Sierra glaciation events. Why do I mention this? Well, because on top of all of that turmoil that we were going through, we also had glaciers present over the last, almost 1 million years, but, more actively in the last 100,000 because of, obviously climate change. But then we had this excessive melt that occurred when the climate began changing again. And when ice melts, it turns into water, and we created this massive, not we, but California's topography, created this incredible chain of lakes that started northern California at Mono Lake, and it was spilling over. That ice would melt and make that lake so full it would spill to the next, the Crawley Lake, and work its way until it ended in a terminal lake, Lake Manly, which would then become Death Valley. And what's interesting with that is that all of those minerals that were dissolved in that water that would travel those hundreds of miles to spill over into Death Valley would all result in the deposit of those evaporites in Death Valley, which is why Death Valley is known not for its beautiful landscape, but for its white gold borax. Borax, what does that even mean to you? You're right, I know. Borax was huge. The Borax 20 Mule team, they would mine those evaporites out after the Death Valley became too dry to have any water in. They would mine the evaporites out and use it for soap. What do you use it for? It's used to make the glass in your cell phones and computer monitors. So we still use that stuff. But nonetheless, when we talk about earlier the different morphology, the glaciation that carved Yosemite Valley, the ice that carved its way through, and the water that drained out and filled, these landscapes and created these inland seas of both not just salt water and fresh water. We've had it all. Volcanoes, earthquakes, subduction, glaciers, rivers, deserts. We have it all in California. This was a lot to chew, I know, and it's just an intro on the beautiful landscapes that were created by the incredibly dynamic geology of California. Please check out some of my field trip videos. I think that will really help paint a picture of all of the diversity that we can observe in your backyard. People come to California to see our geology. From around the world, they come to California to see our geology. I hope this was helpful. Be sure to comment something you liked, a place you've been, a question you've got. Don't forget to like, subscribe, and we'll talk soon.